Yeah. Thanks so much, Corinna, and yeah, all of you for coming here, and especially Madeline and the team for organizing. It's yeah, summer school in the Boston venue. So yeah, I think why are we like showing you like all like this detail here at the beginning? Well, first of all, to give you like an introduction for mass spectrometry, but also because we think it's quite essential to understand many of these settings to kind of yield the best data at the end to then make use of like all the fantastic computational tools we're gonna show you right now. And yeah, I think as of now, most of like the data acquisition strategies and non-target metabolomics built up on data-dependent acquisition. And just to get an idea, who of you has used data-dependent acquisition so far? Who uses data-independent acquisition for non-target metabolomics? Okay, so there's a increasing amount of users, which is great. But yeah, just like to like go back to the basics of PDA. So basically, we want to like do MS or MS to the end, like Rena just showed you, but how the machine or you know that before you actually know. And yeah, in principle, like the trick is super simple. The machine iterates between survey scan and MS scan. And then depending on your routine and the settings you set, you like then select in any subsequent MS event of like such an MS1 survey scan, top n number of things. Right? And then it's kind of like cycled through like this duty cycle, right? And then goes through like different times. And then depending whether you set like a exclusion list after that, with dynamic diffusion, then those ions get excluded, and then the next cycle it goes like deeper, and you get, hopefully get like kind of like all ions that are present at this time. And yeah, like in real time, this happens really fast. And I think here now with like the increase in scan rates of like modern mass spectrometers, we're really like diving into like the cycle. But yeah, there's an inherent problem, and that is subsampling. When you have like a very complex sample, of course, you can only get so many top ion features, right? And then there is always a chance that some are missed. That might be due to like limitations of the duty cycle time, or due to simple mistakes you may have done in like setting up like the CDA routine. So here, as I mentioned already, like DIA, data independent acquisition, is becoming more and more popular, especially like in the proteomics field. It's kind of like a standard now, where you do not do like this like precision on the fly with which ion to fragment, but you just like fragment everything that comes in like the ion at the given potential. And it works that you basically switch with like quadruple for like particular windows. So depending on the DIA method you're using, they're either like large or now they're like getting really small, but like scan rate of like like latest generation of mass spec is tremendously all right, and now here it is just like I think a very great example of how you can like have two types of like different method setups for your DDA routine. So in one here, you did not use dynamic exclusion, method A on your left, and then well, you did use dynamic exclusion on the left side, and you did not use dynamic exclusion on the right, and then yeah, like the machine basically fragments like the same thing over and over again. In this case, you see like very like diagnostic. You see like this line, right? It is perhaps like a certain contaminant, but like always like comes up with same mass, and then the machine would basically spend like scan time over and over again to acquire MSM spectra of these. And then yeah, congratulations. So we now over and over discover again like the same plasticizer, but we're actually wasting scans for the perhaps interesting stuff. Metabolism. Yeah, here it's really critical to set up like your methods like well in order to get like the maximum out of your data. And yeah, to exemplify this, I just want to show a little sample from an Interlab study on dissolved organic matter we were performing, where we kind of like manually inspected like the data structure of like different data sets that were submitted. And here we kind of have three TLCs you can see on the top from Q-top, Q Orbitrap, and then a tribe with Orbitrap lumens. And from a price tag and like performance level, I would say they're kind of like in order. So perhaps like Q-top is like the lowest performing instrument, and then like Q exactly is like the average one, and then like Lumos here is more like the high end. And here on this map on the bottom, you can see already how you get like, so this was exactly the same sample and injected in 3 different instruments. How you can like get like more intensity on MS1 level, right? So here, like the heat maps basically indicate mass versus retention time, and like the more red color indicates like high intensity. So we cover like similar like ranges of like like molecular space in the chromatography. And now if I overlay like the standards that we identified 5 out of 8 standards with Maxis, with like the Lumos, and 7 out of 8 with the Reflector. But then what's, in my opinion, like most interesting is when we indicate the MS-MS events that you're figuring. And I think this is the perfect example of like how like not using proper settings like screws up your analysis. Because you can see, okay, this is like the Maxis here, we cover like a broad range of like molecular space, and like these flu and MS events that are like kind of like all over this map. Then with like the Q exactly the similar but like a little bit more extensive, so we have like a larger coverage. And then with our high-end instruments, you see that there's mainly like these 2 lines. Right? This is exactly what I mentioned before. So they did not use dynamic distribution. And basically what happens here is that they get that's all over again from like the same component that would have been otherwise, excluded, and then would have had enough time to actually cover the interesting stuff. And then, when we then look at like library annotations, we see like quite some difference. Okay, like now the Maxis is like not the best performing instrument here anyway, but we see like a pretty big difference between the Q exactive and the Lumos, even though the Lumos has like the faster scanning Orbitrap and also like a more sensitive instrument. And then like for molecular network coverage, which is here indicated through these nodes, it's just basically the number of features that we detect. There is like almost 5 times different. Even though the instrument is like perhaps 5 to 10 years older and like significantly. Here we really want to like set you up with like knowledge that you when you acquire data, you set up your correctly, because if you have shitty data, then like even the greatest tools that we use don't help too much. And in that context, we performed like a little study, mainly here Paolo, Abser, and a couple of other people, where we systematically optimize these settings for a few examples. And I just want to briefly mention our opinion, like most critical ones. So if you have like happen to have an Orbitrap, they might be useful for you, but also if you have other instruments, I think some of those settings are like perfect. So first of all, I think like the AGC target. So this is basically like the accumulation time that Pravina already mentioned. That is like directly coupled to like the scan, right? And where we saw quite like an influence similar to like mass resolving power. So like the higher your mass resolving power is, the simply like slower your machine scan, and just like the less like data like features you will get. And if we have here like it's very similar, simple like visualization in the form of like this 3 molecular networks that we will learn more about tomorrow in Wednesday. You can see if we have the highest resolution here on the right, we get like the kind of like lowest coverage. So now perhaps for like some molecular formula annotations, the high resolution really helps. So like separating like almost isobars, it helps. but as it makes like the machine slower, obviously you will detect less than if you have lower resolution. So here, even though it's typically like an argument, you know, to buy like the most fancy instruments, yeah, we have the highest resolution, but maybe it's not what actually you would benefit most from. So I think these settings are like important to consider. So yeah, resolution. Then HEC target. So here is basically like the time you accumulate the ions, as I mentioned, to reduce the charge effect. But then yeah, like the longer or like the higher your HEC targets are, like again, like the slower the machine might scan. Similar for like the number of microscans. So this is a setting typical for ion traps, particular orbit traps, but I think also for different computer platforms, you can like kind of like accumulate multiple scans before they actually write one raw scan. And then obviously the higher the number of like micro scans, like the less your scan will be. And then yeah, like how does that also influence not only like the coverage from an MS2 perspective, but also from actually a data quality perspective for your chromatographic feature return. So here we basically indicated 3 fantasy metaframes, which are like acquired at like different like scans. And as you can see nicely, here was like the green one, right? We have like a lot of data, and then they describe like the peak relatively nicely. And then with like the purple one, already a little less, and with the red one is a little less, and then with the blue one it's very little, right? So that you get to like a point that your chromatographic in this situation is not like well defined anymore. And then when you want to use feature finding, for example, with NDMine, that you will learn tomorrow, this has some perhaps ramifications that like the algorithms do not work very well. So not only from like one two perspective that you want to have enough coverage, it's very important to have like proper intercycle times, but also to like actually have enough one survey scan to display the chromatogram like properly. So again, here's the balance, and yeah, depending on how long your HPLC separations are, you know, what kind of columns you use, this needs to be like adjusted to your particular and yeah, here we just display kind of like this time for one duty cycle. The ranges between, in our case here, 0.6 or 0.7 seconds to up to 3 seconds. And then yeah, like I think this highlights already like pretty well what are like the most trivial. So it's yeah, like resolution, like the number of microscans, and then it's the HEC target, and also the top 10 seconds. And I think at least some of them are kind of like universal. So top N is like number of ions that are actually going to be submitted for the data dependent scan. So it's between top 3 to I don't know top 20. You know, so this is like the number of them. Yeah, iterative. All right, and then perhaps the most important one. I was like mentioning it already a couple of times at the beginning, but yeah, please use dynamic execution. So I think pretty much every mass spec platform has like these settings in some form, and yeah, you want to like exclude the ions for like a couple of seconds at least after you apply them, and that's otherwise yeah, you get like these lines and like fragmenting and measuring over and yeah, like looking at like this heat map, it's LTMS maps. It's you find it like quite surprisingly often when you look at like public data that people want to use that. Yeah, really shooting your breath in the question. I think there's one comment.
Yeah, maybe also like I would also use static exclusion. Like just also if you run some blanks and you see that something is in your ACM, something's in your pipes, you know, it's always also nice to exclude stuff. We always feel that we're going to lose out on something that might be the exact same signal, right? But at the same time, if you don't exclude something, you're just going to miss out on so many things. And you can always go back to like requiring if you still have samples, right? But that's like most often like you have to go back to some more experiments maybe.
Right. Thanks for the comment. So for the online participants, you could not hear it well. Robin mentioned that there's also static exclusion to, for example, like an exclusion list. if you know that there is like an internal standard you're infusing, or if you know that there's like certain like background signals, you can also like from the beginning tell the instrument to not background signals. This can come in very handy. I think it's not going to hurt you, but you have to choose definitely dynamic exclusion. All right. Okay, so yeah, this was just like again like the example that I showed you before. That's just the difference dynamic exclusion on and off and things like differences. Okay, and then yeah, last but not least, the isolation width might be also quite important. As you know, like you can like set the quadruple, and I think there's particular differences of like the capability with different vendors, and sometimes this like simple quadruple at the beginning is forgotten because they may have quite some differences in the actual performance. And then obviously this goes very much like together with like then your MSMS quality downstream. And yeah, like what that's defined is basically like just like the MZ window where you isolate the fragment. And then obviously, like if you make this bigger, first of all, you then get like isotope patterns that fall in. But also, if you have a very complex sample, then the chances that like some other ions fall into that same window is more like. And here, thanks to Robin, he actually programmed the precursor purity scanner in the latest version of Day1, where we could test this like systematically, and then yeah, not surprisingly, we see that the overall purity of our MSMS spectra in this complex sample was like go down once we widen the isolation. So now still like all in balance with like the sensitivity, right? So the more narrow you make like this window, then like the less ion transmission you have. And I think like what I like about the two black is that their particle is actually pretty good. So there you get like pretty good transmission even at like the narrow windows, but I know that some other huge platforms, for example, you need to make like this windows wider because they're not like super like efficient and make the narrow and you lose a lot of things. Right here again, I think it's important to like set this properly for your first of all samples, but then also accordingly to get into it. And then one thing that I just want to mention, which is kind of like often forgotten, is that is just like the mass spectrometry. Right? There is a complete different story at the front end, the HPLC system, which I think many of us only consider a sample injection system, but having proper chromatography, of course, is utterly most important. Right? And then we're going to show you this like this night chromatogram where you have like sharp teeth, you like squeeze like this ion in like this like smaller packages. Well, like this tremendously increases your thickness noise ratio. But here, making sure to have like good HPLC, perhaps new HPLC if you have like a proper pumps, you know, that makes things better. Yeah, here it's showed like some like very preliminary results where we were playing around with like 2D and LC separation, and that just like gives you like such higher like quality on the left here, and then according to this, and also like a tremendous increase in library and efficiency. So yeah, like we tend to like think about the fancy $1 million mass specs at the end, but actually like the HPLC at the front end might play quite important role. Yeah. Not going to go too much into detail here, just and then yeah, again, so most of the settings that I just highlighted were from a recent study we did ourselves with like a few examples. But I just want to point out the other papers that came out recently that actually all focus on different instrument platforms. So I don't know if you're working with a FIFA, it might be worth to check those out. But then there was very recently also one coming out in a new Explorers. I think also more in the biomedical background is like examples they look for. But yeah, you may find those useful. Okay, and then I think that's pretty much what we wanted to show in this introduction session. Again, many thanks to all of you for coming here to Copenhagen, and yeah, especially many thanks to the staff of Serum Institute team for organizing this and everything. Yeah, of course, I'd be happy to answer your questions.